Hello, everyone. I'm Robert Bassett. I'm an assistant professor in the Operations Research Department at the Naval Postgraduate School, and I'm presenting here today for the Moore's Emerging Techniques Forum audience. I'm disappointed that we can't be together in person. It's always nice to have an in-person conference and meet some new people and shake some new hands. But I'm also actually presenting for you today across time because this lecture is pre-recorded. My wife and I are actually expecting our first child around the time of the conference. And so if you're watching this pre-recording, it's likely that I am in the hospital with my wife being a labor coach. So anyways, I'm looking forward to presenting today. I want to acknowledge Brian Morgan and Dave Saranchek for the invitation to speak today. I'm looking forward to presenting my work and also outlining some of my concerns in an up-and-coming technology. Uh, in particular, as the title suggests here, so the title being New Ways for Adversaries to Disrupt Neural Network Image Classifiers. So we're going to be looking at neural networks for image classification and in particular some drawbacks and some weaknesses of these tools when deployed in setting with a known adversary. We're going to be sort of red teaming these tools and thinking about how they can be compromised if an adversary wanted to. So at a high level, the primary purpose of this talk is going to be to raise awareness of these limitations, the fact that these tools can be exploited by an adversary given sufficient knowledge assumptions on the adversary. The secondary purpose of this talk is going to be to highlight some of my recent work in this area. So this is from the adversary's perspective. How would we compromise machine learning classifiers? Quick shout out, this work is joint with my former student, U.S. Marine Corps Captain Mitchell Graves, who is now at the Naval Academy. So quick outline where we're going to go. So we're going to talk first about what we use neural networks for, what tasks they do well, and then we're going to follow up by opening up the hood a little bit and talking about what is a neural network generally, just enough so that we can talk about the motivation for some of their weaknesses. And so in talking about some of their weaknesses, we'll be able to specifically focus on how adversaries can disrupt a neural network. And these are, as I say, this is specifically relevant to the Department of Defense and folks who are looking to use these tools in the Department of Defense because, right, we have an adversary which we are constantly thinking about, and so this problem is uniquely situated to affect us. So, what do neural networks do well? I'm painting here with a broad brush, but in general, neural networks tend to excel at tasks which require non-tabular data. And so what I mean by non-tabular data is if you could easily represent your data in an Excel spreadsheet, right? You have each row is an observation, each column is a variable, usually either a number or a category. This is what I think of as tabular data. And so non-tabular data, examples of those I've listed here are things like computer vision, where you're working with videos or images, right? You have data, but putting into an Excel spreadsheet is sort of nonsensical, right? You're losing information to wrap it in this packaging. Another example is acoustics, particularly relevant to the Navy, the Naval Postgraduate School, of course, being my employer. I care about this. And natural language are three examples of data which is non-tabular, and neural networks tend to be state-of-the-art in these fields. Another way of thinking about this is that neural networks tend to excel in problems where we must simultaneously find efficient representations and perform some task. So an example of this is, again, thinking about computer vision. The inputs are going to be individual pixels, right? And individual pixels, where we have this suspicion that, how much an individual pixel affects my task. It's sort of, we have to take these pixels, condense them into something meaningful, and then make a decision from this meaningful representation. And so, again, this is not perfect, but this is a rule of thumb that when I approach a problem, I think of our neural network's going to be well suited for these tasks. And again, I should emphasize, I'm not going to do a deep literature review, but neural networks are state of the art in these fields. So why should we care? Why should we seek to implement them? So this is an old example, but I think it's a telling one. So in May of 1998, the U.S., according to the New York Times article that I have here, blundered on its intelligence and missed India's nuclear tests. So India conducted a series of nuclear tests in May 1998, and the idea was the U.S. didn't see it coming, right? As I say, it's many years old, but in particular, what this New York Times article highlights, as some of its sources have identified, is that um, we actually had surveillance on the test sites, but the weakness is that the images and activities were not, here's the quote here, interpreted clearly or quickly by the CIA, right? And so what um, this was a limitation in the number of hours that analysts could devote to make these decisions, right? Is this important? Is this not important? You only have so many hours in the day that people within here the CIA can spend to identify is something concerning going on. And so what we're saying is we had the technology focused on the site, but we didn't have the tools to analyze those images quickly, even to just triage them and decide here are ones that we need to spend more time on and have a human look at. Here are ones which a machine can quickly say nothing is going on here, nothing has changed, right? So this is an example where having a tool like a neural network for image classification to be able to quickly say, you know, identify a risk, risk of something being developed here, or quickly say, no, nothing is going on, would have been extremely helpful because we could outsource the tasks of identifying um, what needs to be paid more attention to a machine and not have to rely um, on people to do it, right? Or at least be able to supplement people's own judgment. Um, so something a little more modern in its application is in an area where neural networks are relevant is I'll highlight here some ongoing work at the Naval Postgraduate School are naval applications of acoustic vector sensors. Okay, so what I have here listed, what I have showing here on the left is an acoustic vector sensor. Okay, so an acoustic vector sensor is intended to perform the same functions as a sensor array. So just a little bit of background. In general, when you want to detect the bearing of an audio source, you usually require an array of microphones, right? And so ships have these. The idea is you want to come up with some detailed detailed information about an acoustic soundscape. You use an array because it allows you to detect bearing of where sounds are coming from. And so this acoustic vector sensor is intended to replace all that in a single sensor. And what it does is it hangs. This is the sensor here, suspended, and this is of course above water, but when it's deployed, it's underwater. And what happens is this cable is neutrally buoyant, and when a sound actually hits this sensor, it moves a little bit. And by recording the way that this moves, we can actually record which directions signals are coming from. And so here I have listed sort of an X, Y, and Z, some orthogonal axes with which we can measure movement of this sensor, which we can then reconstruct where it's coming from. I'll just highlight some of the people who are involved in this effort at the Naval Postgraduate School, Kevin Smith and Paul Leary in the physics department. And so here's an example. So this is a spectrogram of some audio information from an acoustic vector sensor that Kevin Smith and Paul Leary have deployed in the Monterey Bay near the postgraduate school. And this, so what we have here is time along the x-axis, and along the y-axis we have the frequency of the sound. So higher frequency means obviously a higher pitch sound, lower frequency means a lower pitch sound. Okay, and so what we see here is this spectrogram is actually color coded according to its direction, and so we have this yellow pieces in this spectrogram, which are high combinations of red and green. we have z, which is the z direction is up down. We don't have a lot going on in the z direction. That's a little bit intuitive, but we can actually see here sort of three distinct colors emerging, right? This yellow, this green color, and this pink color. And actually, if you listen to this, you can hear that these are whale calls, and we are able to detect with this acoustic vector sensor three different whales singing to each other on October 27th, 2019. So yeah, it's an interesting application in general, but what I want to highlight here is this is an image, right? So image classification is not just restricted to I stuck a camera on somebody and recorded an image or a video, but any data that we can represent it as an image. For example here, sound, and looking at these colors, we have an application where we can use techniques for computer vision. Specifically, we're going to be focused on neural networks to analyze it. Okay, so let's begin a little bit more of a deep dive. So what is a neural network? Instead of asking that question, let's start with something a little simpler and build up. And so we're going to say, what is a linear model? Okay, so a linear model relates, as you might expect, some variable we want to predict with some predictor. So here I have a single predictor. Here I have some prediction, y. And in a linear model, I have my prediction is a line, a plus bx. It's a linear function of the input, x, okay? And the name of the game is we want to find what are good values, a and b, so that x, the relationship between, I can plug in an x value and get a predicted y value. That's good, okay? So this is a linear model, pretty easy, just line. We want to find the parameters in a line, okay? And a less simple form, but still pretty simple form, we use multiple predictors. So we have p predictor variables, we have a prediction, y, and we want to, again, find the parameters here, these b1, bp's, and this a, this intercept term, that make this linear expression a good predictor. So we plug in our p predictors, we get y. Okay? And so when I'm thinking specifically about images, I want to think about these p predictors being individual pixels of an image. So I want to feed in pixels and then come out with some prediction. Okay? And so here's a graphical representation of the simple example where we have a single predictor and we have an a and b. And so what I've drawn here is an input x, an output, a prediction y, and these arrows, what this means is that when I have every time I have an arrow that's not labeled with an x or a y, this is something I need to estimate. So what's happening is I have something I need to estimate here. This is x contributes to y. How x contributes to y, this is this b term. And then I have this one term, and this one term represents the intercept. So I say the relationship between x and y. Here I have something I multiply by x. Here I have something I multiply by 1, a. Okay? And I need to estimate both of these terms. Okay? The more complicated case where we have multiple predictors, here's a graphical representation of it. So I have these 10 predictors here. Again, we're thinking about pixels just for the sake of this slide. I've limited it to 10 inputs. We have 10 pixels here being input. We have a coefficient, these b terms, to estimate at each one of these arrows. And then we have the intercept term a, and then we have the output y, right? So all of these arrows coming into y represent they're summed when they come in to this y node here. And then again, each one of these input arrows is something I need to estimate. Okay, well, let's build on this. Okay, so these are linear models, and one direction we can build on is right. In general, I'll just go back to this. In general, this y is just some number. In order to do classification with this output y, we're going to we apply some nonlinear function to this y, which turns it into a number between 0 and 1. So the idea is that we turn this y into a confidence that the observation belongs to a certain class. That confidence is between 0 and 1. So large values represent belonging to one class. Small values represent belonging to another class. And so this is how we actually do classification. So we just take these linear inputs, and then you apply some nonlinearity at the end here to make this suitable for classification. We can also have multiple outputs, okay? So I've avoided writing the expressions because it gets a little complicated, but what we have here is, again, 10 inputs. Each one of these arrows is a number to be estimated, and here we have 5 outputs, okay? So these are all constant terms associated with the blue, and coefficients here associated with the black, okay? And so again, if we want to have multiple classes that we want, or if we want to do classification between multiple classes instead of just have numeric outputs that can be arbitrary valued, we apply some nonlinearity to the outputs here in order to do classification. Okay, I say nonlinearity as a distinguisher because, of course, we have all linear functions in between here. All right. So the key to which distinguishes neural networks from linear models are hidden layers. And so here I've just denoted a hidden layer in red. Okay, so hidden layers they're called hidden because they're in an intermediate step between the inputs and the outputs. So we don't actually observe these variables. Okay, and what a hidden layer does is it actually applies a nonlinearity to their inputs. So let's just trace this and describe what's going on here. So we have an input, okay? As this input goes into this hidden node, we have a coefficient to be estimated. We also have a constant coefficient to be estimated. This represents our intercept term, okay? And here, so we have a linear input into this hidden node, and then what the hidden node does is it applies a nonlinearity to its input. And then, after it applies the nonlinearity, that nonlinear output is then fed to y, and we have another coefficient to estimate along with another intercept term. Okay? So what we're doing here is we're chaining together this sequence of linear operations. I have a slope, I have an intercept, and then the hidden nodes give us a little bit of nonlinearity, and then we continue to estimate more coefficients. Okay? In general, you can have multiple hidden layers. So here's a neural network where we have 2 hidden layers of different sizes. And we can see, just drawing these graphics, that this gets kind of complicated kind of quickly, right? So again, each one of these arrows represents a number to be estimated, okay? And we have some nonlinearity here at these hidden layers. And actually, this neural network, even though, of course, it looks sort of complicated on my slide, it's very simple by today's standards. And by today's standards, some of the most successful and state-of-the-art neural networks, for example, doing image classification, have millions of parameters. So these are millions of arrows here. Okay. I'll just say one thing is that the architecture of a neural network is the arrows that connect the different layers. And so you can imagine there are so you can imagine some situations where you would, remove a layer and say, or remove an arrow and say, okay, this input doesn't feed into this hidden layer, only these ones do. And so you can choose, and there's a lot of flexibility there, and this is actually where a lot of research in designing new neural networks is figuring out what are good architectures. Okay? A benefit of neural networks is that this structure is extremely flexible. You can have many layers. You can sort of build this as you wish, and it turns out that actually this simple structure of linear inputs and nonlinear outputs of hidden layers, chaining them together like this, you can there's a lot of flexibility in there. A downside of it is that even with this small example, what is going on in there? If I were to label these arrows with the values that I estimate to be, it's extremely difficult to be able to parse what's going on, right? And the sort of the representation is not intuitive to us. Whereas in the simple cases, in the linear model examples that we were talking about earlier, we can parse what's going on. Oh, this input is going to the output and it has a certain weight. But once you start combining and recombining weights like this, it's hard to know what's going on. And in particular, there is a major drawback, and so this is the main point that I want to make by describing what a neural network does generally, and that is these complex sequence of layers lead to this issue where small changes to the inputs of a neural network can have a large effect on its outputs. Okay, and so what I mean is I can have a situation where x changes, this x1 for example, this first predictor changes a very small amount, but my output would change dramatically, okay, with these y's. And that's bad because, well, to very rarely does this occur in practice in terms of applications that, you minutely change an image, but for example, what you would detect in that image very dramatically changes. And so this is the weakness and the drawback of neural networks that is exploited in adversarial perturbations, which is what we're going to spend a lot of time talking about. So what is an adversarial perturbation? Well, the idea is you perturb an image, so you change an image in a certain direction that causes maximum loss to the network. So the network is trained to do a certain thing and minimize some loss, and you change the image in a way that causes high loss. And when you do this, you have small changes to the inputs, these x's, but large changes to the outputs and the y's. Okay? And what does it actually take to do this? You either need, as an adversary, access to the architecture and the parameters, right? So basically, this graphic, if I'm an adversary and I want to do this, I either have this graphic with all of these arrows labeled with the estimated parameters. Okay? That's one option. Another option is that you have a large numbers of input-output pairs for the neural network. So that is, I have the ability to feed a lot of things into the neural network and see what it does for its outputs. Okay? And if I have that, I can actually construct a surrogate, another neural network which can approximate the original, and I can perform this adversarial perturbation using the surrogate as an approximate. Okay? So you might ask, if this is what's needed, are these realistic assumptions? Right? Is it realistic, especially in DoD applications? Is this assumption realistic assumptions on an adversary, that an adversary, we would have some neural network which perhaps identifies which direction whale calls are coming from, and is it realistic to think that an adversary would have access to all the details of that neural network, or arbitrary number of input-output pairs to train another neural network to approximate it? In general, probably not. If an adversary has access to your entire system, you probably have more trouble than the machine learning considerations are worth. But what this does highlight is something very important, and that is assumptions. And so in particular, trained models, so neural networks that we train, that we find the values that are appropriate on these arrows in the graphics, they're not commonly treated as secrets that should be protected. Okay, right? It's not like, right, we think secrets to be protected. We think about things like cryptography, where you don't share certain keys and things like this, and it's well known that you cannot share this key, or else this technique is not secure and can be compromised. And so what these assumptions suggest is that, right, we should treat trained models as secrets to be protected, because if they get into the hands of adversaries, they can exploit them. Okay. So this is, I think, one of the big insights from this presentation is this work suggests that we should be protecting trained networks more because of the ability to manipulate them. Okay, so quick review of where work on adversarial perturbations has been. So in 2012, Alex Krivetsky, his AlexNet won a certain ImageNet challenge, which this kicked off a resurgence in neural networks. So neural networks have been around for a long time, since at least the late 80s, but they were not thought of as state-of-the-art tools. In 2012, this team showed that they were state-of-the-art for image classification, and so this kicked off neural networks as a topic of interest. In 2013 and 2014, two very compelling papers came out demonstrating that neural networks were vulnerable to adversarial perturbations, where you can make small changes to an input to catastrophically affect the output. The difference between these two papers. So this is the first one that did so. This is this 2014 paper by Goodfellow et al. Showed that you can actually compute them more easily than was previously thought. So the computation is actually not that difficult. 2017, this Carlini-Wagner paper, I mention it because it's a very popular method for generating adversarial perturbations. So just another technique. And let me just list here the contribution that I have with my student, and this is we've contributed some easily computed adversarial perturbations. So this is along the lines of this 2014 paper that showed that it can be done very easily. And these perturbations accurately model human perception of color and texture. So the idea being that you want to fool a neural network, but perhaps if you have a human observer, that the human observer would not notice that the image had been manipulated. And so in particular, we focus in on this color and texture perception of people. So here's an example of our contributions. So on the left here, we have an original image, a source image, which a certain neural network, this is Inception v3 architecture, classifies as a submarine correctly with 99.7% confidence. And on the right here, we have a manipulated image where that same neural network classifies this image as breakwater. So this is a sort of a barrier that's put in certain bays and harbors to make the waves less large. Classifies this submarine as a breakwater. You can imagine why it might be natural to if you're going to misclassify the submarine, to misclassify it as a breakwater, but it misclassifies it as a breakwater with 98% confidence. So again, if you had a tool and you were deploying this tool and you said, well, by minor manipulations in the input image, you go from classifying it as a submarine to classifying it as a breakwater, and you're very confident in your classification. This is problematic if you're thinking about deploying this tool to detect submarines. Okay, I'll say so. This is our contribution is here on the right. If you look very closely, well, can't really detect any difference between these two images. If you look really closely, I've stared at this image for longer than I'm willing to admit. Just on the top of this, the top of the submarine, the blue lines here, you see maybe just a tiny bit of pixelation that you don't have in the original image. But it's extremely difficult to detect, and this is the point. We are accurately accounting for human perception of color and of texture. And so we can break down our contributions in a couple of different ways. So, well, the color and texture way. This is the two ways we break them down. We think about how we should appropriately model human perception of color. This is our color-aware contribution. For texture, we think about we call it our edge-aware perturbations. So, and then we can actually combine them into what we call color and edge-aware perturbations, which are simultaneously accounting for human perception of color and texture. We won't be able to review these details for the sake of time, but we do show in a paper on these techniques that these tools are only marginally more computationally inefficient than the very simplest perturbation method. So you're not paying a lot to be able to account for these things. Okay, so I don't mean to pick on anybody who happens to be colorblind, but this image here represents the issue with human perception of color. Okay, so the problem in particular is that RGB representation of images, where we have red, green, and blue colors, they do not accurately respect human perception. Okay, so what I have here is I've listed I have 3 different X's against a solid blue background. Okay, so this solid blue background in RGB space This solid blue is 0, 0, 1. It is all blue, okay? And what I've done is I've slightly changed the solid blue background to result in these X's, okay? So when I just change the red coordinate from 0 to 0.2, I get this pinkish X. When I change the green coordinate to 0.2, I get this X. And when I change the blue coordinate from 1 to 0.8, I get this red, this blue X. Okay, so we notice that, well, these are equidistant in RGB space. These are each 0.2 away from 0, 0, 1. I can either add 0.2 here, add 0.2 here, or subtract 0.2 here. But when we look at them, we see that we perceive them very differently, right? This one is hard to perceive, this X. This is a little easier, and this is very easy to perceive, right? So this, even though they're equidistant in RGB space, these X's from the background, we perceive them differently. Some are easier to perceive than others, okay? So this is a problem. It's not appropriate to construct perturbations in RGB space. So if you represent an image as a sequence of RGB pixels, it's not appropriate to perturb it there because RGB distance doesn't accurately represent human perception. And so the solution that we used to overcome this limitation is that we used a different color space. So in particular, the CLAB color space. CIE here is French for the International Commission on Illumination, who develops this color space. And in this space, perceived distance is the distance between vectors. So you represent it as in this CLAB space. In particular, you have these lab coordinates, this luminosity, this A and this B. These are how you represent it. And then you can just take the distance between LAB representations, and the idea is that this captures human perception. So just a quick graphical representation. On the left here, I have the RGB cube, which I think most people are familiar with. This white spot here is all red. This is a 1, 1, 1. A lot of red, a lot of green, a lot of blue, and the different corners here. And so the CLAB representation of images is actually a sphere. So we have this A part, which goes from red to green. We have this B, which goes from yellow to blue. And this L stands for luminosity. Okay, so it's just a little different, but the idea is sort of similar to RGB. We represent image using three different pieces of information, and one just does so in a way that captures human perception. Okay, it's a subtle point, but it's important if you want to construct perturbations which are not detectable by humans. So here I have listed, this is the graphic that I just showed a moment ago, the CLAB distance between the X and the blue background. So here the CLAB distance between this red X and the blue background is about 3. Between this one and the blue background is about 17, and so on. So we see that CLAB distance is accurately, at least with respect to the ordering, capturing how we perceive the fact that this one is hard to detect and this one is much easier to detect. Okay. So what we do in order to construct this color-aware perturbation, this perturbation which respects human perception of color, we take an image, we represent it in these lab coordinates, and we construct the perturbation directly in the lab coordinates. And so the goal is to maximize the network's loss by finding some perturbation delta, but we also want to constrain delta to be small in lab space, right? So when we're measuring this delta to be small in lab space, we're saying humans will perceive this difference to be small. Okay. All right. Here's an example of the perturbation directions. So this is a competing method. This is the computationally efficient method that I described earlier. So the source image and the perturbation direction, that is the direction that you would step in to alter this image in a way that you cause misclassification. Okay, and you can compare this, which is a competing method, to our method, which is you can see a lot more awareness of color. Okay, so this is again the competing method and our method. You can see that the texture, the color of the dog is clearly being distinguished, the background and the green grass. Okay, so This is representing the fact that we are accurately constraining perturbations that in a way that the changing color reflects human perception. Okay, so from color aware and thinking about human perception of color, we then thought about human perception of texture. And in particular, so here's this submarine example, which we looked at before, the original image. And here is a perturbation from a different method. This is the original paper that talked about the fact that you can construct these adversarial perturbations. Here we see the perturbation. Okay, so we have here this perturbation, this adversarially perturbed image is misclassified with 44% confidence, and we can see it, right? Now imagine if you had put this kind of change in the waves. It would be much harder to detect because there's so much change in texture going on in the waves, whereas if you put it against the background, our eyes can look at them and say, oh, what is going on with this top of the submarine, right? So clearly texture matters in human perception. Compare this to our perturbation, which I showed previously, and in fact, you can quantify it a number of different ways, but this image actually has more overall change to it than this image. But we've just placed it in a way that it's less detectable. Okay, so we are achieving higher levels of misclassification. Okay, and we're able to place more alteration in the image, but we're just doing it in a way that's less detectable. The way that we will overcome this human perception of texture, that we can't just change all regions of the image equally, is we're actually going to weight the magnitude of the perturbation according to the amount of edge in an image. So here's an image, a bunch of apples here, and here I've applied what's called a Sobel filter. So Sobel filter measures the edginess of a pixel, and so it quantifies the change between adjacent pixels. And so we see certain areas are edges; these are highlighted in white. Certain areas are not edges; these are black. And so the idea is that we're going to constrain perturbations so that they can take higher values in regions with a lot of where we detect a lot of edges, and if we have smooth backgrounds, then we're not going to permit a lot of change in those areas. So here's a quick description. We have a source image. We have a weights from an edge filter. In the previous example, I talked about the Sobel filter. That's one that we recommend in our paper. You have a perturbation, and the goal is to maximize the network's loss, again, subject to constraining your perturbation to be small, where you weight what it means to be small according to the weights from the edge filter. Okay? And so we can actually combine these tools. So the color aware, again, the main idea is construct this perturbation in the C-lab space. Edge aware, the main idea is to constrain the perturbations using the amount of edge that we measure in each pixel. And we can combine them in what we call a color and edge aware perturbation, where we are constructing the perturbation in C-lab space and also constraining the perturbation using the edge weights. Okay. So here's an example. So this is what it's called a targeted attack. So in a targeted attack, you make an adversarial perturbation with the intent of misclassifying as a certain class. So in the previous example with the submarine, our goal was to just cause misclassification into whatever other class. Here, we are performing a targeted attack where we target mobile home as a class. So we have a tank. It's classified as a tank according to this same network, this Inception v3 network, with 85% confidence, and this method, this competing method, classifies it as a mobile home. This was our targeted class with 80% confidence. Okay. If you look, you can actually see, though, the texture of the sky in the background and the texture of the tank. It has sort of these artificial ripples in it, right? Whereas the rocks, for example, if there were these ripples, it's harder to see them there, right? And so In our color and edge aware method, this is what our method on the right. We misclassify as a mobile home with 98% confidence. Again, this is the class we've targeted, and we don't have those awkward sort of distortion on the tank side and in the sky, right? And just I'll flip back and forth a few times so you can see. So this is ours, theirs, ours, theirs, and I hope you can see that it's clear that there's some distortion going on in these images, which is not in ours. Okay. Here's just a high-level outline of these color and edge aware perturbations. So we take an original image, okay? We convert it to grayscale, and by converting it to grayscale, this allows us to compute edge magnitudes. So here we have an image which is classified as a tank. We convert it to grayscale, get the edge magnitudes, and use the edge magnitudes along with this transformation into CLab color space in order to construct a perturbation. And in doing so, we construct this perturbation which misclassifies this tank as an amphibious vehicle. So we were targeting an amphibious vehicle, and we wanted to say, can we misclassify a tank as something that is aquatic in nature? So we achieve it sort of using these steps. Okay, so I will conclude by just summarizing where we've been. So I don't mean to be a naysayer in the sense that neural networks they're amazing. They have revolutionized certain fields, especially computer vision, where they've matured from being sort of a research area to being a mature technology that's implemented, for example, in some very mature computer vision libraries. But they do have a drawback, and that's what I want to bring awareness to, in that if you have complex architectures, they can be taken advantage of by an adversary who knows enough about the network. Okay, and so when thinking about deploying these tools in a DoD setting, it's important to respect this limitation and to keep it in the back of your mind, right? And explicitly, this is a recommendation, formulate knowledge assumptions on your adversary. What is it reasonable for your adversary to know? If they must know nothing, you must treat your trained model accordingly, okay? And so the second part of the talk, we introduced the recent research efforts that I have, looking at specifically constructing these perturbations in a way which properly models human perception of color and texture in a way that the resulting image is then less detectable by a human observer. I will say we spent this talk focusing on the detectability concerns. I mentioned this, but there's more evidence in the reference manuscript, which is they are easy to compute and they cause high rates of misclassification, but you can see references for more details on that. Okay, and so with that, I will conclude. I will thank you all for your time. If you'd like to contact me with questions or anything, I can be reached at this email, and you can see code for this project and a corresponding paper listed here. So, okay, thanks again.